most of the reactions that you've come across in chemistry so far, we've thought of as reactions that just go in one direction. So if you take magnesium, for example, and you add it to dilute hydrochloric acid, we said it reacts in this direction to make a solution of magnesium chloride and hydrogen gas. And we didn't consider the possibility that some of these things might react with each other and go back that way. Because it turns out that in this case, the forward reaction is so much more favourable than the back one that the chances of this going backwards are pretty much negligible, and we call that an irreversible reaction. However, plenty of reactions exist which are not like that, where there's a reasonable probability of going in either direction. So here's an example of this. If we take sulphur dioxide gas and react it with oxygen gas, we can make sulphur trioxide. This is a very important industrial process. It's a key step on the route to making sulfuric acid industrially. But it turns out that that's a reversible process. So yes, SO2 can react with oxygen and make SO3, but there's also a tendency of SO3 to break up and go back the other way. And so you can write this as a reversible reaction. And normally, instead of writing the two full arrows like that just to make it quicker, you write it like that to show that it's a reversible reaction. So we can picture what happens a little bit more if we imagine a graph. So suppose we're going to plot a graph of rate of reaction as a function of time. So let's imagine that we start with a mixture that just contains SO2 and oxygen and doesn't have any SO3 in it. Okay, so that means that if we look first of all at the rate of the forward reaction, it's going to have a high rate to start with because we've got lots of these. Remember, the higher the concentration, the higher the probability of collisions occurring, so the faster the rate. So at the beginning, if we've got lots of this and none of that, then the forward reaction is going to have a high rate. But of course, as soon as it starts, some of this gets converted into that, and so the concentrations of these things decrease. And as their concentrations decrease, the probability of collisions between them decreases, and so the rate of reaction decreases. So this is the forward reaction. Meanwhile then, let's think about what happens to the back reaction. So at the beginning, there was no SO3 in our mixture. We started just with this. So if there is no SO3, there can't be any back reaction. So the rate of the back reaction has to be 0. But as soon as this forward reaction kicks in and starts making some SO3, it will start to be able to react backwards. And the higher the concentration of SO3 that builds up, again, the higher the probability of one of those SO3 molecules breaking up again, just because there are more of them, and so the backward rate will increase. So you get this, where this is the backward rate. And what happens is that that process continues, so the forward rate gets less and less as these things are used up, and the backward rate increases as more SO3 accumulates, and eventually the two rates become the same. And you get a situation that looks like this, where the forward reaction settles down to a level like that, which is exactly matched by the back reaction. And at that point, the rate of the forward reaction is the same as the rate of the back reaction. So all the time, SO2 and oxygen molecules are reacting with one another and turning into SO3, but at this point the concentration of these stops changing, because as fast as they're being destroyed by the forward reaction, they're being formed by the forward reaction, by the backward reaction, and so the rates are exactly balanced, and therefore the concentrations stay the same. And that is equilibrium, okay, where this levels off here. So this is equilibrium, and it means that the rates of the forward and back reactions are equal. And the consequence of them being equal is that the concentrations become constant. Okay, so equilibrium is really important in chemistry because lots of processes are like that. In principle, all processes are. It's just that with this one, the equilibrium lies so far over in this direction that we kind of ignore the backward one. But in principle, everything is reversible. But it's only really when there's a significant probability in both directions that we worry about it. But that happens a lot. And so equilibrium is something we need to understand in a bit of detail. Now, this kind of equilibrium that we've talked about is specifically called a dynamic equilibrium. And what that means is that it isn't true that nothing is happening, because as we said, in the equilibrium situation, although the concentrations of all three of these substances have become constant and they're not fluctuating at all with time, that doesn't mean that nothing's happening, because all the time SO2 and oxygen molecules are reacting with each other and converting into SO3, but it's just that that's balanced by the SO3 molecules breaking back down and forming SO2. So this is recreated as fast as it's destroyed, and that's why the concentrations stay the same. So dynamic equilibrium, that term is there to make the point that it isn't that nothing's happening, but you've got these two opposed processes balancing each other out. And so the key things associated with a dynamic equilibrium that you need to know are, first of all, as we've said, that the concentrations and indeed other macroscopic properties. Macroscopic means things you can measure on the big scale, on the scale that we live on, without looking at what individual molecules are doing. So other macroscopic properties like temperature, pressure and so on, they will all remain constant. Because obviously if the concentrations were fluctuating, then if the forward reaction was exothermic, it might be giving out heat 1 minute, but then as the back reaction kicks back in, it would be taking in heat again and the temperature might go up and down. But no, it doesn't work like that. Once you've reached equilibrium, the concentrations stay the same, and consequently other things that follow from them, like the temperature and the pressure, they stay the same as well. So that's an important thing. And then the second thing we've already stated, but we'll just write it again, is that the underlying reason for that is that the rates of forward and backward reactions are constant, are equal, yeah, and constant. Okay, so it's that equality which prevents the concentrations from changing. The third thing that's important to point out is that this is only possible if you have what's called a closed system. And a closed system means that you've got everything shut up in a box and you don't allow anything in or out. So you can't take away any of the substances or add in extra of any of the substances, or indeed allow extra heat to be put in or whatever. Once you've reached equilibrium, it's got to stay constant. So a closed system is very important. As soon as you have a leak and you allow stuff to escape or you allow extra stuff in, it's likely to disturb the equilibrium. And that's really important because lots of systems are not closed. One of the classic examples of that is to think about yourself as a chemical system and ask what would happen if you came to equilibrium, and the answer is, well, you'd be dead. Okay, equilibrium would be a state in which the various chemical substances that you're made up out of, the proteins and DNA and all that kind of stuff, would break down into smaller molecules. They're not actually in a stable state. So at equilibrium they wouldn't be there, and so you would you would have died and decomposed. The reason you don't do that is because you're not a closed system. So you don't allow your body to come to equilibrium because you're constantly taking in food and getting rid of waste products and stuff like that. So you're not closed off, and that's what prevents equilibrium from happening. So you need to know the key features of a dynamic equilibrium like that. If we think about enthalpy profile diagrams in relation to a reversible reaction like this one, I mean, basically they're the same as for any other reaction. So here's our reactants, here's our product. So this is delta H of reaction, and obviously it's negative going that way, as we've seen for this particular reaction. It's exothermic going forward, and you can see visually in this diagram that if you go back the other way, it's therefore endothermic by the same amount, because you're just doing the same step in reverse. So you could, if you wanted to, say, that's delta H for the forward reaction, and this is delta H for the back reaction, which is equal and opposite. Okay, and that's just a sort of graphical way of seeing that point, but it's not particularly useful, because once you've grasped that point, it's sort of something you don't really need to spell out, because you just know that it's the case. So what we're going to be more interested in is looking at the activation energies on here. So let's just get rid of this, because, as I say, it's not really necessary. We can just say, right, that's the delta H value that's quoted is always for the forward direction. So what we're going to be interested in is what about the activation energy, and we've got used to this idea that there is some sort of energy barrier that you have to go over in order to get from the reactant to the product. You have to go through a high energy state in which bonds are being broken, or at least distorted, at considerable energy cost before you can start making the new ones. And we've got used to the idea that the height of that hill, in other words, going from your starting state to the top of the hill here, that term is the activation energy, the minimum energy that the particles must have when they collide in order for a reaction to happen. Now, in the case of a reversible reaction, of course, you have to think about, well, what happens when you're going back this way? And so this then, instead of just being the activation energy, is specifically the activation energy for the forward reaction. Now, what about the back reaction? Well, it turns out that when you're at equilibrium, you can show that it goes back over the same hill. So it doesn't matter whether it's going forwards or going backwards, the hill you have to go over in between is the same. That's called the principle of microscopic reversibility, and that's one of the many contributions of Boltzmann again, was that he showed that that was the case. So what that means is that if we're focusing on the back reaction, we're going to have this situation. So if we just extend these lines across here, the activation energy for the back reaction means starting from here, you've got to get to the same hilltop, so you've got to get all the way up there. So this is the activation energy for the backwards reaction. Okay, so this kind of diagram is quite helpful for letting you see what the relationship between those three terms is, delta H for the reaction and the two activation energies. And you can express that just in terms of the sort of mathematical relationship between them as delta H. You can see that getting from there to there is plus that term, taking you up to there, and then minus this one, bringing you down to there. So to get from there to there overall is plus that activation energy minus the backward one. So delta H is equal to EA forwards minus EA backwards. And you need to be able to draw that diagram to make this point, but you also need to be able to do calculations based on this. So they might give you any two of these numbers and ask you to solve for the third one. So you either need to memorize that relationship, or it may be easier just to kind of figure it out from the diagram, because you can sort of see, you know, if you're given this number, you know, say this is plus 120 and this is plus 310 or something, and you say, right, well, obviously the difference between these two numbers is 310 minus 120, which is 190, and so you can see that that gap must be equal to 190, and therefore delta H, because it's going that way, is minus 190. So you can work it out visually just by looking at the sizes of the gaps. Or if you don't like doing things visually, you can memorize that equation, but you do need to get that relationship sorted out, and you need to be able to sketch the diagram.